Hello, everyone, and thank you for watching our Expo presentation of the Raspberry Pi. Our device was developed with the sponsorship of Simpson Strong-Tie. Simpson is a leading company in the manufacture of structural connection components, the use of which spans countless residential, commercial, and industrial projects. Occasionally, the installation of these components can go awry, whether that be from misalignments, structural defects, incorrectly sized parts, etc. The task given to us by Simpson is to develop a device to recognize and characterize an incorrect installation of their connectors, particularly their joist hangers. Being able to efficiently verify the correct installation of a joist hanger not only allows a technician to get more done, but it increases the overall safety of the project as well. I will be referring to something called the joist beam hanger interface a lot during this presentation. So for reference, this interface makes up a common construction installation, typically used for flooring and decking. This piece of wood here is called the beam. This piece of wood perpendicular to it is the joist. And this piece of metal is the hanger, which connects the two. Our team has developed a visual sensor that relies on an image processing algorithm. A user will be able to take a simple photograph of the joist hanger of interest, and the sensor will output whether that particular installation falls within tolerance of a safe and correct install. Our hope is our device makes our construction a simpler and safer task. So the project consisted of two subsystems, an image sensor and an image processing program, each with their own subcomponents. Our first subsystem is an image sensor. Based on stakeholder feedback and internal discussion, our image sensor must provide a durable housing for field use, full HD resolution, an ability to communicate wirelessly with a host processing machine for processing, and a rechargeable battery capable of being used for a full workday. A Raspberry Pi 4 Model B fits these requirements. It is a robust embedded system with a plethora of aftermarket accessories and support at a reasonable price point. An 8-megapixel Sony IMX219 sensor was chosen to fulfill the need for full HD resolution camera. Our image processor went through several prototypes and design changes to meet the challenges this project sought to solve. Our first prototype was a Python-based convolutional neural network, which is a branch of machine learning that is commonly applied to analyze visual imagery. And while significant work was done attempting to refine this program, ultimately the amount of training data needed to improve the recognition component of the program proved too much. So we made another prototype. This second one used a Matlab image processing suite called Raspberry Pi Support for Matlab. This suite allowed for wireless communication with a host machine. Connecting to a wireless network via secure shell Wi-Fi allowed for the acquisition of data from the Raspberry Pi's camera, as well as visualization and analysis of said data. This method of communication allowed for rapid changes to the sensor setting and is the method we use most for testing. This prototype relies on feature matching and line detection. So in short, our program would detect a reference, then calculate relevant geometry based on the model of the hanger. The first method we use is feature matching. To obtain an object of reference, the program must know what it is looking for. So using a speeded up robust features algorithm or a SURF algorithm, the outstanding features of a given image are detected and mapped. We feed an image of our object of interest into the SURF algorithm, then feed an image obtained from our sensor and let the algorithm choose prominent points. We then program Matlab to determine commonalities between the two images. Matlab references a database of previously tested and processed hangers we uploaded to determine which hanger model it is analyzing. A Ho transform is then run on the image. This detects prominent straight lines in an image. From the results of the Ho transform, we create a system of lines of best fit around our reference object. These lines describe the positions of the beam, joist, and hanger. Vectorizing these lines allow for the calculation of a dot product between the vectors to obtain the angles between our reference lines. And from these reference lines, we can determine if the hanger, beam, joist interface is installed properly. So with the amount of work that was put into this program and its development, it makes the output seem very underwhelming. When the image sensor is actuated, the program captures and analyzes our image in the process I explained earlier. The processor then outputs a simple go or no-go result that appears on the user screen. A go result means the installation falls within the tolerated deviances of a proper installation, while the no-go result falls outside of this tolerance. A no-go error is accompanied by the likely deficiency noted by our image processing program. And that is our project. That's our project. We are excited to have the opportunity to work with such an established company as Simpson Strong-Tie. And we are so excited to explore other ways image processing and machine learning can help increase safety and efficiency in the construction world. Thank you for listening to our project, and have a nice day.